had released energy from within the atom in the first atomic blast. One of nature's greatest energies hitherto undreamed of, and creating which have confounded mankind. We are apt to think of atomic energy as something new. But God placed this fabulous energy in every bit of matter when he created it. In fact, the earth has been warmed and lighted by atomic energy from the beginning, for the energy of the sun is atomic energy. No, atomic energy is not new. But now that man can control and energy, the world is faced with problems. But the question arises, just what is atomic energy? Well, let's begin back at the beginning. Perhaps it can be said that the cornerstone of our knowledge in this atomic age was laid back in the year 1905, when an unknown clerk in a Swiss patent office scribbled strange equations at his desk. Here, about half a century ago, Albert Einstein gave to the world E equals mc squared. Energy, the equivalent of mass. A radically new conception, key to the atomic age. The idea expressed in E equals mc squared is actually quite simple, but it has caused a great revolution in scientific thinking. It means that any object, this desk, pencil, piece of paper, just any bit of matter represents an unbelievable amount of energy. For example, the atomic energy in, just the paper of this book is the equivalent of the power produced by Hoover Dam in 1 full year of operation, enough to supply the electrical needs of your home for 1 million years. Air is a fragile thing, yet in a single breath is energy equivalent to the burning of 200,000 gallons of high-octane gasoline. Sufficient fuel to fly a giant 4-engined airliner to the moon. Within just the paper of this railroad ticket is enough energy to power a cracked diesel-electric streamliner 3 times around the world. In fact, the atomic energy in 1 pound of any kind of matter, a pint of water, for example, is the equivalent of the burning of 1.5 million tons of coal. Now, of course, this doesn't mean that you can take a pint of water and pour it in the gas tank of your family car, take off on a trip around the world, but the energy is there, hidden down inside the tiny particles of which all matter is made. In order to understand this properly, we must know something about the structure of matter. Matter may exist in any one of 3 states. The same substance may be either a solid, a liquid, or a gas, depending upon its temperature and the pressure. Water is a good example. It may be a solid, ice, or a liquid, or a gas. But even in the gaseous state, it's still H2O. What do we mean when we describe water as H2O? And what does all this have to do with atomic energy? Well, to grasp what this simple formula really means is to understand some of the basic laws governing the structure of all matter. Electrolysis apparatus will help us understand why the chemist has called water H2O. The glass tubes of the apparatus are filled with water from the reservoir above. At the base of the tubes, an electric current is caused to flow through the water from one platinum-tipped electrode to the other. Immediately, bubbles of gas form and go streaming upward. Graduated scales on the tubes indicate the proportion in which these gases are released. On one tube, we read 20. On the other, 10. The greater amount of gas burns with an almost invisible blue flame, hydrogen. The other gas causes a glowing splint to burst into flame. This is oxygen. So we say that water is composed of 2 gases, hydrogen and oxygen, combined in a proportion of 2 to 1. Two particles called atoms of hydrogen are combined with one atom of oxygen to form a molecule of water, H2O. Two colorless, odorless, invisible gases combine to form a liquid. Individual atoms of any substance are much too small to be seen. If we had 1,000,000 of them in a pile, we couldn't even see the pile. You might say, well, if we can't see atoms, how do we know that they exist? Well, there are a number of ways that we can detect their presence. Brownian motion is one of them. If we draw the smoke of an ordinary match into a smoke chamber and then place it on the stage of a very high-power microscope with dark field illumination, we can see something that is really quite amazing. Notice the white spot. They're smoke particles. Why are they moving? They're being buffeted about by invisible particles of air. Air pressure is merely the resultant of untold billions of these particles bombarding an object. At sea level, their combined pressure is 14 7/10 pounds per square inch. That means that on a can like this, there are some 8 tons of pressure exerted on the surface. Why doesn't it collapse? Well, that's because air molecules on the inside are exerting an equal but opposite force. Of course, the velocity of the air particles is determined by their temperature. As the temperature goes up, their speed increases. So let's heat the air inside the can. The air molecules inside the can, here mixed with water molecules, are speeding up. And so some of them are forced out of the can. This smaller number inside, going faster, equalize the outside pressure. But now let's turn the heat off and put the cap tightly on the can so that none of the particles we have driven out can get back inside. As the air inside cools off, these particles slow down and wage a losing battle against the greater number of particles, hammering on the outside, and the can collapses. The effects of air pressure, the movement of the smoke particles, are evidences of the existence of these invisible particles, but certainly they're not the only evidences. For the whole atomic age is built upon certain and positive knowledge of their existence. The atom is not a solid pellet of matter. Instead, it's quite like a solar system. It has a central nucleus and then electrons revolving in orbits about the nucleus. And like the solar system, it's almost entirely empty space. A moment ago, we analyzed water. We found that it was made of two substances, hydrogen and oxygen. This represents the hydrogen atom, the simplest of them all. It has just one electron revolving about its nucleus. The oxygen atom is considerably more complex. There are 8 electrons revolving about its nucleus, which itself is more complex. All of the substances in the material universe, all of the millions of different kinds of things, living and non-living, are made of just a little over 100 of these building blocks of different configuration. Hydrogen, we said, had 1 electron revolving about the nucleus. Well, if there were 2, it wouldn't be hydrogen, but helium. 3, it wouldn't be a gas at all, but instead would be lithium, a silvery white metal. And so we see that these building blocks, which the Creator has made, form all of the material substance of the universe. But in addition, they are also the source of every bit of power in the universe. All of us are familiar with chemical energy. When we light a match, it burns because chemical energy is liberated. Our civilization has been built upon chemical energy. But even with chemical energy, the atom is the ultimate source of power. Only with chemical energy, it is the electrons, the outer part of the atom, that are involved. With atomic or nuclear energy, however, it's the nucleus, the very heart of the atom. Until recently, chemical energy is all that we've known. But on that fateful morning of July 16, 1945, a new age was ushered in as man released nuclear energy for the first time. A source of power millions of times greater than anything we'd known before. Let's see if we can illustrate the difference between chemical energy and nuclear energy. A firecracker is chemical energy. When that firecracker went off, it made quite a fuss, didn't it? That was chemical energy. And you know, it's a good thing it was. If it were possible for us to release the total nuclear energy in the same firecracker, it would equal 10 million sticks of dynamite. That's the difference between chemical energy and nuclear energy. Now, how is nuclear energy released? Well, one way is to split the nucleus in two. Actually break it in half. When this is accomplished, some very strange and wonderful things happen. In the first place, the two halves, weighed together, will weigh less than the whole did before. Some of the mass has disappeared in a burst of energy. You remember our formula? E equals mc squared? The equivalence of mass and energy. To split an atom, we must fire a projectile of the right size and velocity and strike the atom in just the right place. Sounds simple, doesn't it? Actually, it's far from simple. Remember, no one has ever seen an atom. And the target is even smaller. And the atomic projectile is still smaller. To meet the requirements of this exacting task, giant instruments such as the cyclotron have been built, designed to fire a torrent of subatomic particles at the nucleus of the atom. In this model of the cyclotron, steel balls represent atomic particles which are guided in a circular path by a strong magnetic field. Under the influence of electrical forces, the stream of atomic particles spiral out faster and faster until they hit the target at the periphery. But now from the model to the instrument itself, the famous 60-inch medical cyclotron at the University of California. The material to be bombarded is coated on a plate and then carefully mounted in the target assembly. This target is then fixed to the cyclotron in such a way that the beam of high-energy particles will strike it. In the control room behind a protective barrier, the operator puts the cyclotron into operation. Radiation-absorbing lead bolts provide safe temporary storage for the irradiated targets as they await their use in the laboratories of medical research. Probing still further into the mysteries of the atom is the 184-inch cyclotron, also at the Radiation Laboratory of the University of California. This great 4,000-ton instrument spans 56 feet and towers 33 feet above its foundation, and accelerates particles to far greater energies than its 60-inch companion. We are now within the very heart of the 184-inch cyclotron, inside the tank, between the pole pieces of the great 4,000-ton magnet. During operation, this area is a vacuum, traversed by a spiraling torrent of atomic particles, accelerated to velocities approaching the speed of light. In the cyclotron and other accelerators, such as the synchrotron and the bevatron and the linear accelerator, atomic energy can be released, but only in small quantities. These are essentially research tools designed to give us more knowledge of the structure of the atom.
release of atomic energy on a large scale became possible when a method of sustaining a chain of atomic splits in an isotope of uranium was discovered. The production of the first atomic bomb was a frantic race against time. The urgency of war necessitated a whole generation of time being compressed into a hectic 5 years. And it was at a cost of $2,000 million. At the peak of the activity, almost 500,000 persons pooled their efforts under the tightest of wartime censorship. The success of the gigantic undertaking was dramatically demonstrated that morning at Alamogordo when the first white-hot nuclear fires this side of the sun lit the New Mexico hills. 3 weeks after the first experimental blast, an atomic bomb was dropped on the Japanese city of Hiroshima, and then 3 days later, another on Nagasaki. These are pictures of that actual blast that destroyed the city of Nagasaki. 2 bombs have utterly destroyed 2 cities, snuffed out the lives of 150,000 human beings, and ended a war. But still, there were many questions concerning the atomic bomb that remained unanswered. Monstrous scale tests in the Marshall Islands were planned to provide the answers. Into Bikini Lagoon came a fleet of 90 target vessels, led by the venerable old battleship Nevada, painted a gaudy red as bullseye for the target array. Ashore, steel towers were erected to house especially designed scientific instruments and cameras of all types and sizes. Doors of reinforced concrete and lead protected film from the effects of radioactivity. Flying boats joined the huge fleet of photographic aircraft. This was the most photographed event in history. The day of the first test arrives. Observation, weather, and instrument planes take to the air from their base on a neighboring island. The atom bomb is aboard, and it's set to explode above the surface of the water. Destination, Bikini. From the weather plane, blast gauges are parachuted toward the target. Bombs away. Now for the second atomic blast, this one to be detonated underwater. Boarding the firing ship, the USS Cumberland Sound, Los Alamos engineers present their credentials to Marine Guard. Security is the watchword. Aboard this electronic control ship, signals will be transmitted to detonate the bomb. The timing laboratory is a maze of complex electronics equipment, interlocking radio transmitters, automatic timers, and recorders. Transmitters are warmed up and adjusted. Graph cards changed on time recorders. Only 2 minutes to go. The standby signal to all hands. At the central control console, Dr. Marshall Holloway, the leader of the group, throws the switch for the 30-second signal. At the automatic firing board, the last 15 seconds are broadcast.
15
terror-stricken world shifted its gaze from this coral atoll in the Pacific to a parched valley in the Nevada desert. A new and more potent principle, nuclear fusion, was demonstrated in 1952 in the Pacific as the first hydrogen bomb was detonated. This bomb caused a Pacific island 3 miles long and 1 mile wide to completely disappear. And it could do the same to a city.
Power of this dimension at our fingertips, let's think for a moment about the possibilities of the future. Man has within his grasp the power to wipe out civilization and practically destroy the earth in a few days' time. But again, he has the power that can carry him into outer space. For the first time in history, his foot is on the threshold of the vast, illimitable universe. Here before us is a tremendous potential, of benefit or of destruction, of good or of evil. Who will decide which it shall be? Well, one thing is certain, science alone can't decide it. The question will be decided by the people of the world, by you and by me. And the answer will depend upon what kind of people we are. Yes, science has given us a fearful and yet a very wonderful thing to use. How it is used will be determined by things hidden deep down in the hearts of men. Nuclear power is the basic power of the universe. As we step into this awesome realm, we seem to be standing before the presence of the Creator himself. It's enormously important that we appreciate this. And that first of all, we have reverence and respect for the power of the Creator. And now, as never before, we see the importance of faith, of righteousness, and of humility before God, principles upon which this country was founded, and the only principles upon which it can continue to exist. In unleashing the power of the atom, science has set before us a tremendous challenge, and at the same time has brought to our attention the fact that the paramount issue is the rightness of our relationship to God. And every other issue, however important it may be, becomes secondary beside it.